All right, recap video number 8. We are going to be talking about area and volume. So to start, we're going to talk about everything relative to the x-axis. So I have f of x, I have g of x, and I have some bounds from a to b happening here. So to get started, if I think about the idea of area is going to be the collection of a whole bunch of infinitely small rectangles that have heights and widths. Not sure why my pen is being weird, but we're going to go with it. Heights and widths. So when we think about area, if I wanted to find the area trapped between f of x and g of x, the height of each rectangle could be represented with that pink line, which would be f of x minus g of x. And the widths would be infinitesimally small changes in x represented by dx. And I would sum up an infinite amount of rectangles from A to B. So that's how I could find the area that is trapped. But let's say I wanted to find volume of a three-dimensional solid. Well, that volume could be created in a couple ways. We could be created by cross sections, or we could be created by rotation. So if we think about cross sections, that's going to be that we are building up, for instance, squares up out of this plane. The idea of finding volume is that you're going to sum up an infinite number of areas with respect to the x-axis. So let's say I was doing squares. My volume is going to be a whole bunch of squares, so sides squared with respect to the x-axis. I'm going to start collecting those squares at A. I'm going to stop collecting those squares at B. The side of any one of those squares is going to be represented by that pink line of top minus bottom. The same could be said if I wanted to find the volume of a solid, let's say with equilateral triangles. So I'm going to sum up an infinite amount of equilateral triangles from A to B with respect to the x-axis. So if I drew in one representative equilateral triangle, the side of that equilateral triangle is still represented by top minus bottom, f of x minus g of x. Finally, then, I can think about finding the volume by rotation. So I could take this whole area and I could rotate it around, let's say, the x-axis. Well, if I rotate around the x-axis, I'm going to create cross sections that are circular in shape. When I rotate around, I'm going to get a big outer volume created by that f of x, and then I'm going to subtract off my smaller inner volume created by that g of x. So the radius of my inner circle is created by g of x to my axis of rotation. My radius of my outer circle is going to be created by f of x down to that x-axis. But the idea is still finding volume. So I'm going to sum up an infinite number of areas. This time we happen to be circles. From A to B, pi r squared dx minus my inner volume, pi from A to B of little r dx. Well, how big was the big radius? That was f of x minus 0. How big was the small radius? That was g of x minus 0. Remember that your radius always has to touch the axis of rotation. So that's why those zeros are in there. If I changed my axis of rotation, then this bound of my radius would change. If my axis of rotation was up above my area, so let's say I was rotating up here, now my inner radius is this red one from rotation to f of x, and my outer radius, my big radius, would be axis of rotation to g of x. So it would be that red line minus g of x. All of this is still true if we do things with respect to the y-axis. The only thing that changes for us is we're going to be talking about dy. So our integrals are going to go from, in this case, 0 till 1 on the y-axis, dy, and everything I would talk about, let's find area first. Everything I talk about is still going to be drawn in, for instance, our rectangles. This then creates our width of our rectangle, and our heights are infinitely small with respect to y. So there's our heights. Our widths then, I need to figure out from this point minus this point. So my greater x value minus my lesser x value, my change in x's. On the right, I have this curve, x cubed. Y is equal to x cubed. But I need to talk about this as a function of y. So that's going to be the cubed root of y is equal to x. So cubed root of y minus my f of x is y equals the square root of x, which would be the equation y squared equals x. So minus y squared. Notice that this is a change in x compared with a change in y. Up here, when my pen was a lot bigger, we had a change in y as multiplied with a change in x. So we're still doing the same thing. We're just switching around our variables. Everything with respect to y will be the same that we did with respect to x, except every single piece of your integral has to be with respect to y. Likewise, if we were to do a volume, let's say I wanted to do volumes that were cross sections of quarter circles. So the area of any 1/4 circle is 1/4 pi times the radius squared, but I want to be with respect to the y-axis. So I'm going to start at 0. I'm going to stop at 1. This pink line that I found before, that should have changed to pink. This pink line that I found before is my right curve, cubed root of y, minus my left curve. All right, AP Inspired Understanding. This comes from a free response. I don't actually have the names of the functions written down, and that's because I just want to talk about the understanding. So we're going to call this top function f. We'll call the bottom function g. It's supposed to be in orange. And then you want to store your intersect points. So you'll find whatever A is and whatever B is, and you'll press stow as A and stow as B. So that way, when you are calling them back, you don't have any rounding errors. So to find the area of the shaded region enclosed by the graphs, you could paint from top to bottom, in which case your area would be from A to B, whatever you've stored, and then you can just write f of x minus g of x, all of that with respect to the x-axis. Now, you could paint from right to left, but then you're starting to introduce values that pertain to y, which again, not impossible, but I don't necessarily think that's as efficient as doing our x's when we've already found our a's and b's and stored them. Find the volume of the solid generated when we rotate around the horizontal line of y equals -5. So if y equals -5, if I were to draw in my rotations, because I'm revolving, this is going to be my little r. This would be my big R. So my volume is going to be pi times the integral from A to B, big R squared minus little r squared with respect to the x-axis. Volume then is going to be pi integral from A to B, whatever I've stored, big R squared minus little r squared. And of course, you can write this as two separate integrals if you'd prefer. My big R squared is going to be, in yellow, is going to be f of x minus my axis of rotation, which is -5, top minus bottom, which is -5. My inner radius is going to be my g of x. My colors just do not want to change today. I apologize. G of x minus -5. Now, this says to actually find the volume. So if we had our calculator, we would just do math 9. If you had to do this by hand, it's probably a little bit messy, and those functions hopefully would be nice for you, but you actually would want to go through and find the volume. But again, I'm just trying to get your understanding here. The last thing then, region is a base of a solid. Each cross section is a square. Find the volume of the solid. So our idea of volume is that we're going to sum up an infinite number of, in this case, squares perpendicular to the x-axis. So that's now I know I want dx. If I go back to my graph, my volume then is going to be from A to B, of a side squared with respect to the x-axis. Each one of those squares has a side that is represented by top minus bottom. All right, last one is for you to try for yourself. It says the base of a solid is the region in the first quadrant bounded by the graph of y equals x squared and the x-axis. So we've got y equals x squared in the first quadrant and the x-axis. So this is the line y equals 0 between 0 and 1 for x. So this is the line x equals 1. Here is my region, maybe. Come on, pen. There we go. Here is my region. And I would like to find the volume of each cross-section that is a semicircle. So I'm going to draw in semicircles that run from top minus bottom. What is the volume of the solid? So go ahead and set up your integral. 1/2 pi r squared dx. We're going from 0 to 1. This is supposed to be my radius. Well, my diameter is top minus bottom. So my radius would be top minus bottom cut in half. Take a second for yourself and do this one by hand to find the volume. Pause your video and try to do this one by hand. All right, I came up with 1/8 pi times x to the 5th over 5 evaluated between 0 and 1. So when you plug in 1, you'll get 1/5 times 1/8, which leaves you with 1/40th, or pi over 40. All right, the next thing then is the recap video of an FRQ that you can watch going over a funnel. Just remember, we want to think about area is the idea of finding infinite number of rectangles. When we get to volume, that one rectangle side, that one representative top minus bottom, now becomes the side of a triangle, or the diameter of a semicircle, or the radius of a quarter circle. Or we're going to end up rotating, and we're still going to use a representative radius when we talk about pi r squared.